America's biggest oil-producing basin is called the Permian. Every day, it produces about 6.6 million barrels of crude oil, nearly half of all U.S. output. But crude oil is not the main fluid brought to the surface. Across the Permian, oil and gas operations generate roughly 22 million barrels of salty water every single day. For every barrel of oil, 3 to 4 barrels of water. That is almost enough to cover the daily water use of New York City. This water is not an accident. It is a normal working day. Where does an ocean of water come from in the middle of a desert? And where does it go? The industry calls it produced water. The same porous rock that held the oil for millions of years also holds ancient brine, some of it possibly trapped down there since before the dinosaurs. It is 3 to 5 times saltier than the ocean, salty enough to leave a white crust on steel valves. Some of it was added by people. Hydraulic fracturing pumps water down the well, and in the first weeks, part of it flows back. Then, a simple rule takes over. In many mature wells, oil production declines, while water becomes a larger share of the fluid reaching the surface. The well keeps working, but more and more of what it delivers is brine. What comes out of a wellhead is not oil. It is a mixture: oil, gas, salt water, sand. The first machine it meets is a separator, a long steel cylinder lying on its side. No miracle filters inside, no centrifuges. Gravity does the work. At the inlet, the stream slams into a plate and the gas breaks free and rises. The liquid drifts along the vessel and settles into layers. Oil is lighter, so it gathers in the middle. Water is heavier, so it sinks to the bottom. Level sensors, valves, and internal baffles hold the boundary. 3 exits. Gas goes to a pipeline, oil goes to storage tanks, and the water leaves through a third pipe. That third pipe is where a system begins that almost nobody has heard of. The Permian's oil has its own pipelines, terminals, and tankers. But in the same desert, a second network of pipes runs alongside it, a water network. Gathering lines reach out to well pads across the basin. Pump stations push the brine onward. Trunk pipelines merge it into flows the size of a river. Tank farms provide millions of barrels of buffer storage. One company, WaterBridge, operates about 2,500 miles of water pipe, roughly the straight line distance from New York to Los Angeles, and that is one player among many. All told, thousands of miles of pipe here were built not for oil and not for gas, but for wastewater. Right now, WaterBridge is building a pair of 30-inch pipelines called Speedway across the northern Delaware Basin. The initial phase is designed to carry 500,000 barrels a day. An announced second phase would double that total. Both are meant to carry brine. Analysts estimate that the Permian will account for roughly $100 billion in water management spending through 2030, an entire industry that never makes the news. Its product has almost no outside buyer, and you cannot simply leave it on the surface. So, where does it all go? The water has 2 roads. The first road leads down. Most of it, around 16 of the 22 million barrels a day, is injected back underground. Not where it came from, but into disposal wells. Deep, porous layers, already filled with natural brine. There are thousands of these wells across the basin. The second road runs in a circle. Brine can be cleaned just enough to be used for hydraulic fracturing again and sent to a new well instead of fresh water. In 2021, the biggest operators covered about a third of their frack water demand this way. By industry estimates, recycled water now covers about 60% of that demand. One company, Select, reports an industry record: 500,000 barrels of treated water delivered to a single frack job in a single day. Large recycling complexes handle hundreds of thousands of barrels a day. So the system seems settled. Part goes down, part cycles back. But the underground route, the one that takes most of the water, has started running into trouble. When operators inject millions of barrels into the same deep formations day after day, pressure rises. If an ancient fault lies nearby, water lowers the friction, and rock that stayed silent for thousands of years begins to move. In many U.S. oil regions, the most concerning induced seismicity has been linked not to hydraulic fracturing itself, but to the long-term injection of enormous volumes of wastewater. And only a small share of disposal wells causes noticeable seismicity. West Texas felt it anyway. In December 2022, a magnitude 5.4 earthquake, among the strongest in Texas history, struck near the edge of a seismic zone north of Midland. The regulator expanded the zone, kept deep disposal shut down, and imposed limits on the nearest shallow disposal wells. Then, in February 2025, a magnitude 5 quake hit a completely different part of West Texas, in Culberson County. It did not mean every well was dangerous. It showed something else. Cheap space underground depends on more than the volume of rock. It depends on pressure, on depth, and on the distance to faults. Since June 2025, new and amended permit applications for disposal wells in the Permian have faced tougher review. A wider area examined around each well. A hard cap on injection pressure, where the operator must prove the water will not break the sealing layer above the formation. And a daily volume limit calculated from the pressure inside the reservoir. In parts of the Permian, regulators are restricting how much water certain disposal formations can accept. What does that mean in practice? The water has to be moved farther, into new trunk lines, other districts, less convenient formations. Every extra mile means pump stations and energy. Industry consultants forecast that, over the next few years, the cost of gathering and injecting water in parts of the Delaware will rise by 20 to 30%, up to $1 per barrel. $1 per barrel sounds modest, until you remember that every barrel of oil here comes with 4 to 5 barrels of water. Water has not stopped the oil, but it is now one of the basin's biggest operational questions. It has become a growing line item and an engineering problem that can no longer be solved by drilling another disposal well. Then, the industry asked a question that would have sounded absurd not long ago. What if this is not waste? The first idea: desalinate it and give it to the desert. Easier said than done. This brine is several times saltier than the ocean, and standard reverse osmosis, the workhorse of seawater desalination, becomes inefficient or simply uneconomic at that salinity. Engineers are testing freeze desalination, where growing ice crystals reject the dissolved salts. Texas Pacific Land is building a research facility rated at 10,000 barrels a day and quotes a target cost below $1 per barrel. A goal, for now, not a proven commercial price. The second idea is stranger: the salt itself. Permian brine carries dissolved lithium and magnesium. The Department of Energy is funding programs to recover critical minerals from produced water, and in February 2026, Element 3 reported that its Midland facility had produced lithium carbonate from Permian brine on industrial equipment, not in a lab flask. Water that the industry spent decades pumping back underground is starting to be treated as a resource. But here is the arithmetic that matters. Recycling really could become the main source of water for new frack jobs, yet existing wells keep lifting more brine than new wells need. Even if every new frack job ran on recycled water, millions of barrels a day would still have to be injected, desalinated, or moved somewhere else. The problem is not solved. It has simply stopped being invisible. Come back to that West Texas sunset. The whole world calls this place an oil basin, but most of what rises to the surface here every day is water. Ancient brine, pumped up together with the fuel. The oil can be sold and carried away through pipelines. The water remains the basin's responsibility. So the industry built a second, invisible system to manage it. Thousands of miles of pipe, pump stations, treatment plants, deep disposal formations. The future of America's largest oil-producing region may depend not on how much oil it can extract, but on what it does with its water. 22 million barrels a day, moving through a system almost nobody notices. Somehow, it works.